week 6 discussion section. This will be more on the propositional logic and the logic and computers chapter, that's chapter 9 and 11 from the textbook. Let's start with propositions today. So before we start with propositions, let's look at the interesting uses of or, the word or. I think this is the first page of chapter 9. It's interesting to talk about this. So let's look at the first statement, which says that you can take this deduction if you are at least 18 years old or live in Arizona. So look at the word or, right? So or is, here you don't need to say that it's like you have to be 18 years old or live in Arizona or both, right? So this is self-explanatory that if you're 18 or above or live in Arizona, you can take a deduction. So this is the first usage. The second one was you can take a lump sum payment or an annuity. So it's either one of them, right? You can take either one of them. So this was you can be 18 or live in Arizona or both. This one is you can take a lump sum payment or an annuity. So that's either one of them. The third one is either you stop doing this or you will be in big trouble, right? So that's a logical consequence, right? That's an implication that you better stop doing this or you will be in big trouble, right? And that's like if you don't stop doing this, then you will be in big trouble, right? So this is like a consequence. So there are three usages of the word or, and that's really interesting to note, right? Okay, so let's go to propositional. What are propositions, right? So a proposition is a statement or a sentence which is either true or false. So it needs to have a truth value. I think we've covered it in the previous discussions that if a statement has a truth value, only then will it be a proposition. So example, the sun rises in the east, right? That's a true statement. So it's a proposition. Um, if I say that drop the ball, it's not a true or false statement. Like that was an instruction, not a statement, right? So that's an example of what a proposition is and what a proposition is not. So a propositional variable represents any arbitrary proposition. So propositions are represented by the symbols any capital letters, usually PQR, and the propositional variables are represented by small letters. That is, here we write it as PQR for any propositional variables, right? All right, a few operators that we need to know. This is the not symbol, negation. So if I write not P, so this is the negation of P. This is the or symbol, so this is P or Q. That's also called the disjunction. Now we have and right there. So that denotes and, so that's P and Q, or the conjunction. So disjunction is P or Q and conjunction is P and Q. This is if then Q, so that's an implication. So if P then Q can also be written as P implies Q, right? If P then Q. Here P is called the premise and Q is called the conclusion, right? So that's about the different operators we have. A few more operators that we can talk about are exclusive or, implies, and equivalence, where this is P, X, or Q. That is either P or Q but not both. P implies Q is if P then Q. So if P is true, then it will be, if Q is true, then this holds true. This is equivalent. So if P, if and only if Q, it can also be stated as if P then Q and if Q then P. So we'll look at this in the future in the next slides, but this means that so if you're asked to prove P equivalent to Q, you have to prove that if P is true, then Q is also true, and vice versa. So if P then Q and if Q then P, right? So that's P if and only if Q. You have to prove both ways. Assume this, prove Q, assume Q, prove P. Okay? Alright. Precedence of operators, as we have in division, multiplication, arithmetic, and subtraction, we have the same thing, that is not and or, XOR, that's exclusive or implies, have the same precedence. Because logically they can be handled together, but this is not and or, XOR, implies. It's also called the closeness of the operator. That is the word that is being used in the book, right? Okay. Next thing is the truth table. It represents the truth values of a compound propositional formula. Each row corresponds to a single truth statement, and if the result for at least one of the assignments is true, it's called satisfiable. Otherwise, it's called unsatisfiable. I'll just give you an example of what the truth table is. Right here. So you're given this is a table where you have put the propositional variables. It's P, Q, P. So they're the propositions that you put in. That is P or Q, P and Q, the complement of P, the complement of Q, and P exclusive or Q. Right? So that's a truth table. It represents the truth values of a compound propositional formula. Each row corresponds to a single truth assignment. So here, originally you assign truth variables to truth values to the original variables, that is P and Q. So if you're given a very complicated propositional formula, you break it down as much as you can and go to the atomic propositions. That's P and Q. That's the variables, the propositional variables, and you assign all the possible values that they both can take. So here we have two values that a variable can take, that is true or false. That's why it's a truth table. It's true or false. So we start with giving both of them true, one of them true, that's right here, and then both of them false. Okay. All right, so that's what a truth table is. So if a propositional logic is true for all cases, it is termed as a tautology. If for all cases it is false, we call it a contradiction. Okay, so two words that you should have in mind: what a tautology is and what a contradiction is. All right, so let's try to look at this. So you're given PQ. Now this is the truth table. Let's populate the table. So let's look at P or Q, right? P or Q. So when you talk about P or Q, it's like, let me just write it here. Okay, no. So yeah, P or Q states that either of them is true, then the result would be true. So true and true, true or true would be true, right? True false would also be true, because at least one of them has to be true for this to be true. False or true, again this is true, but false or false will be false. So the statement is that either P or Q are true, then P or Q will be true. Okay, so that's that. Okay, next statement is P and Q. So both of them have to be true for this to be true, otherwise it's going to be false. The first one is true and true, so that's true. The second statement is true and false. One of them is false, right? So it becomes false. Again, this becomes false. False or false and false is also false, right? So that's the second one. Okay, let's go to the third one. That's the complement of P. The complement of P is just that whatever value you have, that's the complement of it. So like, just change that value. So true becomes false and false becomes true. And similarly for QC, the true becomes false, false becomes true, true becomes false, and false becomes true again. All right, let's look at P exclusive or Q. So that is, whenever either one of them are true, this becomes false. Okay. So if both of them are the same value, this becomes false. So it's going to be true or exclusive or true will be false. True exclusive or false would be true, because they are two different values right here. Okay, so that's why we have true on both of them. All right, let's do the next question. This is P implies Q. So here P implies Q would be true if, this is a good case. So if P then Q. So if the first statement is, let's take an example for this. Let's say P is it rains, Q state it gets humid, right? So if it rains, it gets humid. If it rains, it gets humid, then P implies Q is true, because P is happening and Q is also happening, right? So P implies Q is true. Now it is raining, but it is not humid. But my statement states that if it rains, it gets humid. So this is false, right? Because it is raining, but it is not humid right now. So this is false. Now the third one is, the proposition is false. So it does not rain and it gets humid. But since I don't know if it rains or not, this statement is true. Now this is the weird part. Weird is when P is false, right? So if P is false, the value will always be true for everything, because if your if condition is false, the statement becomes true no matter what. The value of Q does not matter anymore. Okay, so again, true if P then Q. So if P is true and Q is also true, then the statement held true because it is raining and it is humid. So the statement was true. If it rains but it is not humid, then the statement did not hold true. And if it did not rain, it doesn't matter if it was humid or not, it just stays true, right? So yeah, that's P implies Q. Let's go to P is equivalent to Q. So let's write that down. Okay, so that is when if P then Q, the same thing which you looked at the implication, look at the equivalence. So if P is true, then Q has to be true. If Q is true, P has to be true. So that's if and only if, right? That's how you write it. If P then Q and if P then Q. So you have to check for both of them. So P then Q is satisfied if both of them are true. Perfect. Is P implies Q satisfied if P is true but Q is false? No. Does this make sense? Let me just write it down for you. So this will be P implies Q and Q implies P. So for the second statement, what happened was this was false, because true false for P and Q gives an implication value of false, right? So this became false. So false and whatever value this could be would always be false, right? All right. Next one is P is false, Q is true. So this implication is true. But then Q implies P becomes false, and then T and F becomes false again. And since F implies false is true for both of them, this remains as true. Okay? So this is an interesting thing that we built on from the implication properties. Okay. Next up is not P, and we're getting a formula for P implies Q. So let's just state that we are supposed to prove that P implies Q is equivalent to not P implies not P or Q, right? So as I said, when you're given a propositional formula, you try to build up the truth table of that and show that if both the values are equal in the column, so if both the columns are equal, then the propositional formulas are equal as well. So let's start with PQ and let's populate not P, right? So not P becomes a negation of T of P. So that's false, false, true, true, right? That's false, false, true, true. Now you're supposed to make an OR, a disjunction of not P and Q. So not P and Q, like you just do a disjunction of these two values. So this is true, false. So that's true. If it's true or false, this is always true. False or false is false. True or true is true. False or true is true. Right in the variables, it's true, false, true, true. Now the implication values. So when true is true, when P is true and Q is true, P implies Q will be true. So it's false only for when when P is true but Q is false. That's only one time when the implication is false, right? Otherwise it's always true. That is when P is false, then it remains as false, right? So look at the two columns where P implies Q and not P or Q, which both of them are the same. So they're equivalent, and hence you can prove equivalence of different formulas using that. Okay. Next one is propositional formulas. So a propositional formula, a formal description of it is that any variable, any propositional variable is a formula. So this is a really interesting way of writing the definition of this formula down, because it's a bottom-up approach. So the first one is that any propositional formula variable is a formula, and the basic operators that you can talk about, that is if, that's and, or, and not, all of them are propositional formulas. Like if alpha and beta are formulas, then you can build up as alpha and beta, alpha or beta, and not alpha or not beta will also be formulas. And it's an interesting thing to note that almost all propositional formulas can be narrowed down as a combination of and, nor, or, and not or, right? So yeah, so you can define if a particular given form description is a formula or not. Okay, there are three different kinds of laws that we've studied about associativity. So you can prove this by using a truth table. And I think that's one of the homework questions, where you can just have a truth table with columns alpha, beta, and gamma. Write down alpha, beta, alpha or beta, and then have alpha or beta, which is again ORed with gamma. And then the similar thing with here, that is have beta or gamma, and then alpha or beta or gamma, and just show that the two columns are equivalent, that is all the values for all the combinations of true false are the same. One more thing I would talk about is make sure you have all the values factored in, that is for alpha, beta, gamma you have true, false, true. So like each variable can take two values, that is true or false, so you'll have 8 values that you'll have to show the truth table for. Okay. So commutative laws are again like if you change the order of the operator usage, that is alpha and or alpha or beta or alpha and beta would be same or would be equivalent to beta or gamma, beta and gamma, right? So here you see CL1 and CL2. Distributive laws. Now this is interesting to this helps a lot of proving in the future that if it's alpha is is a conjunction with a disjunction between beta and gamma, that will be equivalent to two disjunctions between, that is alpha beta and alpha gamma, and conjoined together, right? So here you see this. Like always keep these in mind, because these are the distributive laws are I think the basis of discrete math in the future. So yes, so that's that. Any formula alpha of a propositional logic defines a truth function phi a, that is a function that takes bit arguments and produces a bit value. A truth function is commonly called a Boolean function. So like, yeah, a truth function will always be defined for a propositional formula. So just have that in mind as well. I think one homework question is related to these. Okay, let's go to the logical operators. This is where we start chapter 11, just for people who think who want to break the video down for. So arithmetic operations that computers work are worked in bits and are logical operations. So when you talk about the working of a computer, most of you would know this, but a computer is basically just like operations of zeros and ones, and whatever high level languages we code into is eventually goes down to zeros and ones in the assembly code. All right, the simplest pieces of computer logic are gates. Now they're taken like they're usually between 2 bits, and you get a response out. So that's like x. This is an x or y gate. This is an x and y gate. Now if you okay, we'll talk about this. So this is x or y. This is x and y. This is the exclusive or y. This is not x not, right? So this is not, and you usually have a not symbol, the bubble in the front, right? So if I put a bubble here, that becomes nor. So not or, this becomes not and if I have a bubble here, right? So these are the most basic gates, or and not and XOR. Yeah. So gates can be chained together to produce complex results. So now XOR is usually written as x and not y conjoined with disjoint with not x and y. So that's right here you see x and y. So the first one is an AND gate, but AND gate with a not y. So again there's a negation of y which goes into the AND gate right here, and here the negation of x goes into the AND gate with a value from the y variable, which both of them are joined together for the OR gate that goes for the x or y, right? Another way to write x or y is x not x is conjoined with not y, and both of them are disjoined together So they both are almost same formulae, but you write it down as this using the same um, input. You don't need to use two inputs for that. You just use the same input and you use the bubble right there, right? So this just changes the variable to the opposite one. So why, if this is true, the variable, the value that is fed into the AND gate is actually false. If it's false, it becomes true here, right? This acts as a NOT gate. Okay, next thing is binary representations. So numbers are represented as zeros and ones. So when you talk about numbers that are in decimal, you write them down as 0 to 9. So like all the numbers that you can show with the digit 0 and 9 are called decimal numbers. And the binary numbers are usually 0 and 1, right? So 0 can be represented as 0, 0, 0. 1 is represented as 0, 0, 1. 2 can be is represented as 0, 1, 0. 9 is represented as 1, 0, 0, 1, right? All right, so as a number is written in decimal, it's usually 9820. So 9820 is, so 0 goes to 0 into 10 raised to 0, 2 goes to 2 into 10 raised to 1, 10 raised to 2, 10 raised to 3. So each digit is, so this is 9820. That's how it is written down. Similarly for binary, if there's a number of this form, you just write it down as b0 into 2 raised to 0, b1 into, so it's always from the left hand side, from the right hand side, right? This is how you write it. So if you're given a number 1001, you know how to break it down as and like get the decimal value out. Okay, the binary arithmetic is, so if you have 0 plus 0, it will be 0, 0 plus 1 again will be 0, 1 plus 0 is 1 because it's commutative. Addition, binary arithmetic is commutative. 1 plus 1 is 0, but there is a carry that is 1, so it's carry forward like we do basic addition as well, right? So add 1 to these numbers, that's 0, 1, 1, 0. So what is this number? This is 0, this is 2, 4, 8. So let's add 8, 4 and 2. So that's 16. This number is 16, right? See, you make mistakes. All right. So you add 1 to that, you get 17. So this is 1, 2, 4, 8. Add 1 plus 2 plus 4 plus 8. That's 17. Add 1 more to 17. And so 1 plus 1 is 0. Now I get a carry here of 1. Now that carry is added to this binary number. So you get 0 and again a carry. 1 plus 1. So again is 0 with a carry 1. Again 1 is added to 1. You have a 0 and a carry 1 here again. So you have 1, 0, 0, 0, 0, right? So that's how you carry forward. That's binary addition. Finding the equivalent decimal number, we talked about this. So if you're given this decimal number, you need to find this. So you just open this up. So 1 is multiplied by 2 raised to 0. 0 is multiplied by 2 raised to 1. This 1 is taken in as 2 raised to 2, 2 raised to 3, 2 raised to 4, and 2 raised to 5. Right? And that's how I wrote it down, and you get the value of the decimal number. Okay. Here, what we're looking at is our half adders. What they do is there is no C in, like there's no carry that they take in. So if I have inputs x and y, the sum should be x, well, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 will have a sum 0 and a C out. That's a carry out, right? So here you see the gates, right? So this is the sum value and this is the carry value, the carry bit, okay? So that's what we were talking about. 0 plus 0 is 0, 0 plus 1 is 1 without a carry, 1 plus 0 is also 1 without a carry, 1 plus 1 is 0 with a carry 1. A full adder adds 3 values, that's x, y, and the carry in. So if you have 0 and 0, you add 0, you will get 0, 0. Again, if there is a carry in, it becomes 1. Now the interesting part is here, when you have an x that is 0 or y that is 1, that gives out 1, but then the carry in would make it 1 plus 1 again. So that is 0 and 1, right? Let me just write it down right here. You see it here, right? So 1 plus 1 becomes 0 and 1. Now the best one is the last one, 1, 1 and 1, which will have x and y added together. That will give us a carry forward of 0, carry forward of 1 and a sum of 0. but that sum would be added to the cin, that will give us 1 here, and a carry out, that was 1 right there, right? So that's a full adder and a half adder. And yeah, so in this discussion we discussed about propositional logic, what variables are, what operators are, the precedence of them, the priority of them. The truth table, we did a few questions, very basic questions on this time. What P implies Q is, what P equivalent to Q is, that is P if and only if Q. We prove a very basic formula that P implies Q can be written as not P or Q. Then we discuss what a propositional formula are and how it's a top-down approach, sorry, bottom-to-top approach. We discuss associative, commutative, and distributive laws and how to remember distributive laws. What truth functions are. We discussed the basic gates that we know of, and, or, nor, not, NAND, and XOR, and we complex results are also written down from the basic gates that we know. We discussed how binary representations are done and how to convert a binary number to a decimal number, and what a full adder and a half adder usually acts like, right? So that's discussion for week 6. And please let me know if you have any questions on my email address, and best of luck. Thank you.